Good morning and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We will continue with our module 2, that is DER Integrated Distribution Network Modeling. We have seen the models of the DERs, we have seen the model of loads, voltage control devices. So, now the major thing which is connecting all of them, that is the distribution feeder and line model. So, this is the exact 3-phase line segment model first we will develop, and then we will go for the simplified model and henceforth. So, generally we model the 3-phase distribution system as a pi model, what we normally have seen for transmission network as well, that you will have a series impedance and the shunt admittance is actually segregated into two part or bifurcated in two part, that you have Z in series y by 2 at one side of that Z and y by 2 at the other side of the Z. So, same architecture we follow for distribution system as well. So, this is your series components for the 3 phases and this is your shunt component for the 3 phases. Now, there is a difference between this transmission and the distribution network model. Generally, in the transmission model, we considered them to be a balanced system. That means, we model them as a single phase model. We normally follow the single phase model. But for distribution networks, they are mostly unbalanced. Very few distribution networks are balanced. It may be the primary distribution network. Never ever your secondary distribution network will be balanced, because you have a single phase laterals, you have single phase loads, you have two phase loads, you have two phase laterals. So, your mostly your distribution systems are unbalanced in nature. So, this is your Y bus matrix, where it is a 3 cross 3 for one bus between I and J. Okay. So, this is your shunt admittance one, this is your current 3 phase line current I line R Y B, this is your line impedance, this is also a 3 cross 3 matrix which represents Z R R. These diagonal elements are the self elements and these off diagonal elements are the mutual impedance. Okay. Then you have current injected at node I and node J, and this is your voltages at node I and J. So, keeping this into mind, we will start deriving our 3-phase line segment model. So, this is our model. First, we will apply Kirchhoff's current law at the node J. Okay, that means at this point. So, what are the currents? Your incoming current is to this point, these two are same. So, we will see this one. So, you have an incoming current, that is your I line, your outgoing current is I j plus your shunt current. Okay. That shunt current will be because of its own phase current and also because of this mutual admittances between two phases. So, this is y r r v j r plus y r y v j y plus y r b v j b. Okay. Similarly, for y phase and as well as b phase. So, r y b, you got your 3 line current expressions. So, if you represent it as a matrix form, you see I line r y b equals to I j r y b plus half of y r y b and v j r y b, just representing these 3 equations in a matrix form. Now, we will apply the Kirchhoff's voltage law on this system. So, if we apply Kirchhoff's voltage law, we can see that V I R, that means this voltage V I R plus V J R, this is your V I R voltage, this is your V J R voltage. V J R plus self impedance multiplied with the current of that phase, that is Z R R into I line R plus this mutual impedances Z R Y of the other phase current, that is the I line Y, similarly with the third phase. Got it? So, this is your voltage for a one phase. Similarly, you will see the voltage for the second phase, you will see voltage for the third phase. So, these are the 3 KVL equations per phase you will get after applying your Kirchhoff's voltage law on this circuit. So, if you represent this in a matrix form, we will get the equation 10.2, which is V I R Y B equals to V J R Y B plus your complete 3 cross 3 Z matrix multiplied with your line current of that phases. Got it? So, now in this equation we have this I line in 10.2 and we have derived the value of I line in our 10.1. So, we will put that value from 10.1 to the 10.2. So, if you put it, then this will become your modified equation, that your V I equals to V j plus your Z matrix multiplied with your I line component. Now, do the rearrangements and you can see that if you take the V j R y b common from this and this two, like this one and this one. If you take this common, then you will get U, that is the identity matrix, plus half Y R I B plus Z R Y B multiplied with your V j plus Z R Y B multiplied with your I j R Y B. So, can you see the similarity with our transmission network model, where we represent the VSIS in terms of A, B, C, D parameter of VR, IR, right. This is your sending end voltage, sending end current, this is your receiving end voltage, receiving end current, and that is represented with the transmission network 2 port network parameters with to represent the sending and receiving end voltage and current. So, VRYB, that is your sending end voltage, VJRYB, that is your receiving end voltage, and they are related with this matrix. So, we can represent it as an A matrix. Similarly, IJRYB, that is your receiving end current. So, this ZRYB will be represented as the B matrix. So, this is your A and this is your B matrix for the 3 phase line segment. So, we have represented the sending end voltage in terms of receiving end voltage and receiving end current. Now, we will see the next one, that means you have to represent the sending end current in terms of receiving end voltage and receiving end current. So, how to proceed with this? So, previously we have applied Kirchhoff's current law at the receiving end. This time we will apply the Kirchhoff's current law at the sending end. Okay. So, what will be that? Your IIR, that is your sending end current, equals to this I line R plus, similar to that previously we have discussed, that with the shunt also you will get the current with the self shunt component and as well as the mutual shunt component with the other phases. So, this is the that current, and same for IY and IB. So, these 3 equations similarly you can represent it as a matrix form and you will get IIRYB is equals to I line RYB plus your VI RYB. Okay, got it? This is your sending end current, this is your sending end voltage. Again, you have an I line. We derived this I line equation in our equation number 10.1. So, that value we will put again in this equation. And if we put this, then we will get this is your I line, this is your I line matrix. If we put that value plus you have this portion, again you do some arrangements, rearrangements, you will, this is your receiving end current, this is your receiving end voltage. So, take these things common plus you put this VIRYB we have derived the sending end voltage also in 10.3. So, put that sending end voltage equation here and you will get this revised equation, okay, which is receiving end current plus half of y into V plus half of y into identity matrix what you got into Vj plus z into I. So, simplify this equation, take the receiving end voltage terms in one side and receiving end current terms in one side, you will get this simplified version. So, this is resemblance with your ABCD parameters. Okay. So, this is your C, sorry, this is your D and this is your C, because this is your VR, IR, right. So, you arrange it accordingly with the receiving end voltage and the receiving end current and you will get your C and D matrix. So, we have represented our 3-phase unbalanced distribution network with its equivalent pi model corresponding to its ABCD parameter, which is the conventional transmission network model, what we have used for medium line transmission line modeling or maybe long line approximated pi model modeling, which is normally used for determining the sending and the receiving end depending upon the voltage and the current values. So, generally in case of overhead lines, the capacitance value is less, that we know, that is even for transmission system, that is even true for distribution system as well. So, this y RYB is close to 0 generally, that means your capacitive reactance is very high, your capacitance value is very high. So, capacitive admittance is close to 0. Then your A and D will reduce to only identity matrix, your B will become Z matrix and your C will become 0. So, can you see this resemblance? This is actually a short line. This is actually a short line. So, we have came from a medium line equivalent and we derived, if we neglect this shunt component, we came to a transmission network short line component. Only the difference is that there your B matrix is a Z matrix or Z value, which is a balanced quantity. Here it is a 3 cross 3 matrix, only this is the difference and everything. This is also a 3 matrix, 3 cross 3 matrix. Okay, this is also a 3 cross 3 matrix. In transmission network, your A and D equals to 1. In distribution network, it has become an identity matrix. In transmission, your B is equals to Z. Here that Z has become a 3 cross 3 Z matrix and there C equals to 0 and here it has become a 3 cross 3 0 matrix. So, that is only the difference. Otherwise, you can see the resemblance between the short transmission line and an unbalanced distribution line, because the distribution line length is not very high, it is close to 30 kilometers, 20 kilometers or 40 kilometers. So, we can think it as a short transmission line. Okay. This is the modified or you can say simplified version of the 3 line segment model. Now, we will approximate that. We know that the unbalancing effect, whenever till it is balanced or this thing, then it is fine, but whenever if you see an unbalancing effect, you will see a mutual coupling. In the Z matrix also we have told that it is a 3 cross 3 matrix. What is this off diagonal elements? These off diagonal elements are actually the mutual coupling impedances. That makes your analysis very difficult whenever you have a mutual coupling. So, to get rid of that, generally we use sequence transform. We are familiar with these things in case of a fault, because fault makes a balanced system unbalanced. To catch that unbalancing effect in a balanced form, we take the sequence component out of it. The same thing we do for unbalanced distribution network. So, sequence components are mostly used to represent any unbalancing effect. If it is a balanced system and you get a fault, that makes the system unbalanced. So, there we do the sequence component analysis. Same thing, even at the normal operation of the distribution system, you can use that sequence component to represent your unbalanced distribution network. So, this is your system. We have done it for a simplified version with a balanced system, where you can see the decoupled circuit will get. Okay. That means, though you have a mutual coupling, but if you give a balanced system, how the sequence component will become an decoupled system. So, this is your original one. So, you can make it a positive sequence, this is your positive sequence, this is your negative sequence, and this is your zero sequence component. Okay. So, we will do the analysis for the simplification, we will do the analysis for the balanced version, and we will see how this sequence component analysis makes that whether you even for your balanced condition, this Z is a 3 cross 3 matrix for an at least for an unbalanced for a distribution network. So, that will become a decoupled scenario. So, we use the alpha operator, which is given by this matrix AS. You can represent the phase voltage in terms of the sequence component matrix, and similarly the inversion that we know from our fault studies. And then your voltage, if you use the same KVL, this V RYB equals to Z RYB, you put the AS matrix and your actual impedance of your sequence component impedance is given by AS inverse Z RYB AS. If you calculate, then you will just get a diagonal matrix. That means, you get rid of your off diagonal elements. Okay. Means from your system, because generally your system you have a mutual impedance, but if you convert that to a sequence component from that unbalanced or balance, whatever. Balance means it is already you are getting a single phase one, but if it is an unbalance, from there if you go to that sequence component level, you can see that your with the sequence component impedance matrix does not have any off diagonal elements, you have only the diagonal elements, and that diagonal elements makes your each and every component separate from each other. So, we will put that value in our equations. We will think normally we know for the overhead power lines your positive and negative sequence impedances are equal, let us see that is Z plus, and your zero sequence impedance is Z 0. If you put that values in this matrix, you will get this phase matrix. Okay. That means, your phase impedance you can calculate with the help of your positive, negative and zero sequence components. And then this is your voltage KVL equation, you have VIR. We have neglected the capacitance effect that I have already mentioned before. So, this is your sending end voltage is equal to your receiving end voltage plus your total current and impedance. This is your Z RYB multiplied with your current IJR, this current. This is the same current I line and IJ. So, if we do the simplification on a per phase basis, we have seen that we can see that VIR equals to VJR plus 1/3 of this is VJR, this is VIY component, this is VJB component. That is same what we did for unbalanced system as well. So, then you add this term and subtract this term from this equation, like this term you will add here and this term you will subtract here. So, you will get this simplified version Z 0 minus Z plus, then IJR, IJY and IJB. Okay. So, your actual equation will become the sending end voltage is equals to a receiving end voltage plus your positive sequence impedance multiplied with that phase current. This is your IJR, R phase current only, plus your Z 0 minus Z plus by 3 multiplied with the summation of this 3 phase current. IJR plus IJY plus IJB. Similar, you will see the same effect in the Y phase and the B phase as well. So, now this portion is separate, this portion is separate. Now, what is this current? You have a 3-phase supply with a neutral. This is your R, this is your Y, this is your B. So, you have your IR, IY and IB phase current. The plus of this is actually your neutral current. How much it is coming from here? This is actually your neutral current. So, you have got your voltage expression in terms of that phase voltage at the receiving end, your that phase current only plus a certain coefficient with your neutral current for each and every phases. Now, for balanced condition, obviously this neutral current is 0. Okay. So, neutral current if you make 0, then this complex equation what we have derived for the system, that can be, and a coupled phase model can become a decoupled sequence model. This is for the balanced. If it is an unbalanced, then your IN will be greater than 0, right. So, by knowing only your IN value, you already know this Z0 and Z plus value. So, you will get your actual phase voltage. You need not to know, or you do not need the information of that mutual coupling impedances, right. So, those impedance value you get rid of your voltage equations. So, that makes your life easier. So, a coupled phase model has become, if we convert, this is for the sequence model only for the balanced. If we make it for the unbalanced, then how it will become? VIR equals to VJR plus Z plus IJR plus your Z0 minus Z plus by 3 of IN, right. That means, by measuring only the neutral current and phase current and the receiving end voltage, you will get your sending end voltage, right. So, this is your unbalanced system, you can easily model with the help of sequence component. And your approximate 3-phase line segment model, what is actually looked like this without the shunt admittance. Now, you can transform it to a sequence impedance model, where you have a Z plus positive sequence line impedance and a Z0 minus Z plus by 3 amount of impedance at the neutral wire. So, this is your current in the phases, and the neutral wire is experiencing the current of IR plus IY plus IB. So, if it is a balanced, then this current will become 0. If it is unbalanced, then this current will be greater than 0. Just to measure, by measuring your neutral current, you will get your phase quantities. So, that makes the approximate 3-phase line segment model more attractive rather than your actual phase models, because these are mostly decoupled model, because you have seen this equation does not have the IY component or IB component. That means, other it is not, does not depend upon your other phase current, it depends upon your neutral current, how much resultant neutral current it is flowing in the neutral wire. So, with this I will end today's lecture, and we will continue with the modeling part with the power model of the distribution line in the next class. Thank you.